Okay, getting a little bit of a late start this morning. I intended on getting on at 6. I woke up at 5, but then I just wasted 2 hours of my morning basically. Which is a bummer, but I am here now. Check. Mark. Bam. This goes at 7. Sorry. And I'll mark this as time that I wasted. I guess I should have known that this was a risk, given that I didn't have gym this morning, that I was just lazy around in the morning and not get started. So it wasted an hour, probably hour and a quarter really. But yeah, last night this arrived, which is the new Ghidra book. Ghidra is a reverse engineering tool, decompiler, disassembler, binary analysis tool that is created by the NSA. It's open source, runs on the JVM. Open source competitor to IDA Pro, although from what I understand I've never used IDA, but IDA Pro is vastly better. It's more of the industry standard. But given that I don't want to pay for a bunch of proprietary software, I figure it makes sense to invest in open source technology, because while IDA Pro is the industry standard and it has an advantage over Ghidra, I think Ghidra is relatively newcomer. Ghidra. It's a free and open source reverse engineering tool developed by the National Security Agency of the United States. The binary was released at the RSA conference in March 2019. The source code was published 1 month later on GitHub. So yeah, 2019. It is funny that they release binaries first. Like, who the fuck is gonna trust a binary from the NSA? I mean, I run it. It could have NSA mischief in it. It probably does. But I guess it's technically open source. Hopefully it doesn't. But I mean, if you're gonna get owned, I think getting owned by the NSA isn't the worst thing in the world. They're an incredibly powerful state actor, and I reside in the country in which they are purport to protect. So, if they wanted to own every single electronic device in my life, they probably could. So using their tools to disassemble some programs, I think, is a fair trade for that breach of privacy. I'm just messing around. I doubt that they have a malicious code in their tools. Anyways, the binaries were released at the RSA. Yeah, I read that. Ghidra is seen by many security researchers as a competitor to IDA Pro. The software is written in Java using the Swing framework. I've never used that. I've used Spring before, but fuck, man, I hated that shit. It's annotation hell. For the GUI, the decompiler component is written in C++. Oh, cool. And is therefore usable in standalone form. Interesting. Scripts to perform automated analysis of Ghidra can be written in Java or Python via Jython. Those features extensible and supports other programming languages, is accessible via community plugins. Plugins adding new features to Ghidra itself can be developed using the Java Basic Extension Framework. What if you use Kotlin and other JVM languages? If it's just JVM compatibility, probably. Ghidra's existence was officially revealed in the public Vault 7 in March. Public via Vault 7 in March 2017, but the software itself remained unavailable until its declassification and official release 2 years later. Some comments in the source code indicate that that it existed as early as 1999. Wow. Well, I mean, you'd expect them to have their own tools for doing this stuff. Let's see here. Gidra's existence. Yeah, we read that. High-level changelog, version 1, proof of concept. 2, database, docking windows, Slate decompiler, version control, scripting, version tracking, file system browser. First unclassified version. First public release. Graph visualization, new PDB parser. What is PDB? Program database, format developed by Microsoft for storing, debugging information about, so it's like Dwarf for Windows, but a program more commonly, program modules such as DLLs or EXEs. PDB files commonly have a .pdb extension. PDB file is typically created from source files during compilation. It stores a list of all symbols in a module with their addresses and possibly the names of the file and the line which symbol was declared. The symbol information is not stored in the module itself because it takes up a lot of space. The debugger itself, Rust and Go binary support bsim. I guess it's because Rust and Go have different ABIs than C. So it's probably a decompiler support if I venture guess. 2024 Swift and Dwarf 5 support macro improvements. Cool. In June 2019, Core Boot began to use Ghidra for its reverse engineering efforts on firmware-specific problems. Following the open source release of Ghidra software suite, Ghidra can be used as a debugger since Ghidra 10. Ghidra debugger supports debugging user mode window programs via WinDBG, Linux programs via GDB, and macOS programs via LLDB. That's one thing I would like to experiment with because, fuck man, using GDB CLI, it can be a complete pain in the ass for analysis, like rapid analysis. If it's a program that you want to spend a lot of time with and get to know really well, then yeah, doing your own like GDB. But the problem is that the layout ASM GB2E feature like just fucking glitches out constantly. Like if it was reliable, then I would be happy to use it, but it's just completely unreliable as a way of viewing the disassembly. So you have to constantly be running disassembly if you don't use the 2E, and then the disassembly usually, for some large functions takes up multiple pages, so it's really frustrating. It's like with Delve, more familiar. I have more experience with Delve because I've done so much Go programming in the past. With Delve, you can just like disassemble the area that you're around really quickly, and it just gives you the area that you're around the program counter, not the entire function that your program counter is inside of. All right, supported architectures. The following architecture by NF4 is supported. It's pretty large support, but I mean most things are going to be these two guys, and then a long tail. I guess Java bytecode. What is DEX bytecode? Oh, it's a Davik virtual machine. I guess they have their own bytecode. eBPF. Oh, nice. Some of these architectures I've never even heard of. Binary Ninja. Yeah. Okay, cool. Well, I just wanted to get a little bit of background on Ghidra. I'm not going to be reading this book anytime soon, but I did buy it because it's a second edition. It was just released, and I do plan on reading it at some point. How many pages is it? It seems like a beefy boy. Yeah, I mean it's pretty beefy. It's close to 600 pages here. So I might just read part 1 and part 2 to get me bootstrapped onto using Ghidra. Part 3 is extending and customizing it. Part 4 is a deeper dive. So part 1 and 2 would take me to just page 217. So that's like more of a reasonably sized book. Part 4 is a deeper dive into loaders, processors, the decompiler itself, real world applications, patching binaries, easier for IDE users. Yeah, I think I get a lot of value out of just getting the first 2 parts of this book read. But yeah, not on my agenda anytime soon. So I will go ahead and toss that into the stack. Alright. So we left off last night. We watched the lecture for the linking section, and he just has one lecture on it, on linking, and it's a whole chapter. So I mean, they're cruising through this material. Like, I guess they expect students to read 2 chapters every week. That's kind of like the pace at which they're going through the material in the book. And there's no way that students, especially with like other classes and other coursework that they have to complete, can keep up with a pace of reading 2 chapters each week. Because I mean, these chapters are like 100 plus pages. I mean, I guess, you know, I can do that. I can read a chapter a day if all I'm doing is reading. But like, if you expect them to read and also do practice problems, which is what the book asserted at the beginning, is that like, as you're reading, you should be doing the practice problems. Don't come back and do the practice problems after you read it. And it's like, bro, like, you're cruising through these lectures. Like, it's a 2-month course, I believe. It was September and October are the 2 months that they did the course. And if we look back at my learn log, I'm just gonna kill this stuff, and I'll kill this because I'm done. Actually, it's kind of cool logo. I like that logo. It's Ouroboros dragon. Anyways, if we go back over to here and say, hey, learn log. If you look at my schedule, like, I've been doing this book now for 5 weeks straight. Granted, 2 of these weeks I took like, I went 3 weeks hard, 2 weeks not so hard. 2 weeks of recovery from the 3 weeks of going hard. And when I was going hard, I was doing almost all of the practice problems and being really rigorous. Whereas now I'm just like, I can read a chapter a day because I'm not doing any of the practice problems. But if we think about it, we're on chapter 7. We're 755 pages into the book. The book is about like 1,100. So we're over halfway in, and we're about halfway through this. So at this rate, I will complete the course in my estimated time allocation here in Q2. It would be 1, 2, 3, 4. It would be a month or 4 weeks into Q2. But I don't want to spend all that time, to be honest. Like, a lot of the subject matter in the latter part of this book is stuff that I'm very familiar with. Like, the first section, I kind of was familiar with that stuff already. I guess the virtual memory stuff is coming in the latter half, and that isn't stuff that I'm very familiar with. I think linking and virtual memory are the 2 areas that I really want to shore up my understanding of. System I/O and concurrency and networking. Like those three sections, while they're very important, I spent a lot of my life doing IO, doing networking, doing concurrency. So I'm not going to probably get as much out of that. Additionally, I have a whole book on concurrency that is much deeper than anything that this book can approach. And that is scheduled for August, September here. The C++ concurrency in action book. So yeah, I'm not going to I'm probably just going to skip that section. Or maybe like leaf through it, see if there's anything that jumps out at me. But yeah, my ambition is to actually complete this course in the next 2 weeks. So only take 2 weeks of April to complete the course. And that requires me to go at a very fast rate of reading, a very fast rate of actually completing the lab work, because I'm not going to skip any of the labs. And then also it's going to require me to like skip all of the practice problems as I'm reading. And I think that's just the nature of the beast. Like the same thing happened with the Linux programming interface. Like I started doing that. I was doing all of the exercises, and I got to maybe about mid-January, and I was just like, I am not going to finish this. It's going to take until like March or April if I just like keep on going at this pace. So that's when I started just skipping the exercise at the end and just reading for understanding and doing a few exercises here and there when it felt like I should do something to shore up my understanding. But yeah, all right, let's start on linking then. I'm only going to be doing about 30 minutes of reading before I get breakfast here. But yeah, I like to get started. Let me grab my cell phone because I want to send a photo to my accountability pod. I'll be right back. Let me go ahead and send my... Okay, let's pull up the text here. Boom, boom, boom. Okay, linking. Linking is a process of collecting and combining various pieces of code and data into a single file that can be loaded, copied into memory, and executed. Linking can be performed at compile time when the source code is translated into machine code, at load time when the program is loaded into memory and executed by the loader, and even at runtime by application programs. On earlier systems, linking was performed manually. On modern systems, linking is performed automatically by programs called linkers. Wow, it was performed manually? I guess at some point everything was performed manually, right? Linkers play a crucial role in software development because they enable separate compilation. Instead of organizing a large application into one monolithic source file, we can decompose it into smaller, more manageable modules that can be modified and completely compiled separately. When we change one of these modules, we simply recompile it and relink the application without having to recompile the other files. Linking is usually handled quietly by the linker and is not an important issue for students who are building small programs in introductory programming classes. So why bother learning about linking? Understanding linkers will help you build larger programs. Programmers who build large programs often encounter linking errors caused by missing modules, missing libraries, or incompatible library versions. Unless you understand how a linker resolves references, what a library is, and how a linker uses a library to resolve references, these kinds of errors will be baffling and frustrating. Understanding linkers will help you avoid dangerous programming errors. The decisions that Linux linkers make when they resolve symbol references can silently affect correctness of your program. Programs that incorrectly define multiple global variables can pass through the linker without any warning in the default case. Programs that incorrectly define multiple global variables can pass through the linker without any warnings in the default case. The resulting programs can exhibit baffling runtime behavior and are extremely difficult to debug. We will show you how this happens and how to avoid it. Understanding linking will help you understand how to avoid scoping rules. How language scoping rules are implemented. Interesting, scoping rules. Do they mean with static? Is that what they mean by scoping rules, or do they mean like lexical scoping inside blocks? I think they mean stat. Yeah. For example, what is the difference between global and local variables? What does it really mean when you define a variable or function with a static attribute? Understanding linking. Let me wrap up my headphones here. Understanding linking will help you understand other important system concepts. The executable object files produced by linkers play key roles in important systems functions, such as loading and running programs, virtual memory paging, and memory mapping. Understanding linking will enable you to exploit shared libraries. For many years, linking was considered to be fairly straightforward and uninteresting. However, with the increased importance of shared libraries and dynamic linking in modern operating systems, linking is a sophisticated process that provides the knowledgeable program with significant power. For example, many software products use shared libraries to upgrade shrink-wrap binaries at runtime. What does that mean, shrink-wrapped? So many web servers rely on dynamic linking of shared libraries to serve dynamic content. I guess that's using DLOpen. All right, so you guys, example program 1. This example program consists of two source files, main C and sum C. The main function initializes an array of ints and then calls the sum function to sum the array of elements. This chapter provides a thorough discussion of all aspects of linking, from traditional static linking to dynamic linking of shared libraries at load time. One thing I do want to do, and I've done this a little bit, but now that I'm getting deeper into linking, is in Go has this concept of packages, and packages get compiled into archive files. I want to take one of those archive files, blow it up, and see what the actual object files inside of it contain, because they have a bunch of rules, and Go has a bunch of rules as far as like exporting based on the case of the symbol and like the symbol's first character, and then also rules around test packages. Like usually every Go source file inside of a directory is typically part of the same package, but then you also have an underscore test package that's kind of separate from that. Does that get compiled in a separate compilation unit? Is it a separate object file? How does all that like work as far as like the actual archive files that are produced? I think the test package actually gets a separate archive file entirely. But is linking a mechanism that's used to control visibility of symbols? That's another thing I'm kind of curious about. Okay, so I might do that later, just to better understand Go's archive files. But that's really an implementation detail of the Go tooling, and I think they changed that format. But yeah, I'm kind of curious what it is, how they do that. This chapter provides a thorough discussion of all aspects of linking, from traditional static linking to dynamic linking of shared libraries at load time to dynamic linking of shared libraries at runtime. We will describe the basic mechanism of using real examples, and we will identify situations in which linking issues can affect the performance and correctness of your programs. To keep things concrete and understandable, we will couch our discussion in the context of x86-64 system running Linux and using the standard ELF64, hereafter referred to as ELF object file format. However, it is important to realize that the basic concepts of linking are universal. Regardless of operating system, the ISA or object file format details may vary, but the concepts are the same. Compiler drivers. Consider your C program in figure 7.1. It will serve as a simple running example throughout this chapter that will allow us to make some important points about how linkers work. Most compilation systems provide a compiler driver that invokes the language preprocessor, compiler, assembler, and linker as needed on behalf of the user. For example, to build the example program using a GNU compilation system, we might invoke the GCC driver by typing the following command into the shell. So we say GCC optimize debug output to prog main C and sum C. Figure 7.2 summarizes the activities of the driver as it translates the example program from an ASCII source file into an executable object file. If you want to see these steps for yourself, run gcc-v. The driver first runs the C preprocessor, which translates the source code of file main.c into ASCII intermediate file main.i. Let's go ahead and run with -c. I've never done that before. Or -v, is it? -v, yeah. Let's mkd our chapter 07. And then I need to find a makefile here. Oops, makefile. And then copy from chapter 05 makefile and chapter 05 .gitignore into chapter 07. And then I cd into that directory, and then I'm going to vim the makefile here. So the thing that we're going to do differently is we're going to use GCC, and we're going to use OG, and we don't need this thing, but we will need the -v. Looks good to me. And then we can say vim, this is going to be main.c, and this is going to have int sum for declaration. Int, I'm going to do this as a header. So we'll say vim sum.c, and this is going to have int sum. I'll do it my style. So this will have int star a and a int n, and we would say int. I don't like doing that. We'll say auto s is equal to 0, and we'll say int s is equal to 0. Why not return s? And we say for auto I is equal to 0, I is less than n, I plus, yeah, whatever, I plus. And then in here we just say s plus equals a sub I. Okay, you want int here as well. Great. So that's a pretty straightforward sum. I'm going to say copy sum.c to sum.h, and we're just going to delete all of the implementation. We'll just leave that there. And then we're going to open up main.c, and here we're going to pound include. We're going to include sum.h, and we're going to have a main here. And this guy is going to return the invocation of sum of array 2. And we'll have our global here, int array of size 2 is equal to 1, 2. Okay. And of course we don't need any of these arguments here. Oh, sorry, needs to be quote string like that. Okay. And if we open up makefile, we're gonna have to fix up this makefile. So this will just be main.c. And then we'll say main. We're going to depend on main.c, and we're also going to depend on main.o. Sorry, sum.o. And those are going to go there. Our target's going to be there. And then we have to have one for libraries. Sorry, I need to pull this up here like that. So this is going to be sum.o. This actually needs to be build sum.o. This will be just sum.c. And yeah. We also want to include here sum.h. I don't typically see that though. Alright. Even though it does technically depend on it. So here we're going to say dash O is not. We're going to say dash C. Like that. I think that's what you do. Man GCC dash C. C is, wow, there's so many fucking options to GCC. It's insane. So I never read this man page. You can't read it. There you go. Compile or assemble as source files but do not link. And then dash O is place the primary output in file. Files applies to whether sort of output is being produced, whether it be an executable file or an object file. Okay, so we can still have our dash O here if we want. Okay. So we take in sum C and produce build sum O. Looks about right to me. And this takes in build sum O and main C and produces build main. Okay, let's go ahead and make makefile. And sorry, program binaries are going to be build main make. Okay. So first we do the sum compilation. ZSTD, bam. ZSTD is just like massively successful. It's amazing. Okay, these are all the arguments, and then I guess there's a bunch of arguments that were added. Well, it's nice. It tells you where the search paths are. Alright, and now we're actually building the main. I don't see it actually invoking the different tools or where it actually stores the files. The driver first runs C preprocessor, which translates C source code file main.c into ASCII and intermediate file main.i. In some versions of GCC, the preprocessor is integrated into the compiler driver. Static linking. The linker combines relocatable objects to form an executable object file program. This is CPP, other arguments. It gives us our.i. Next driver runs the C compiler CC1 to translate main.i into an ASCII assembly language file, main.s. Then the driver runs assembler, which translates main.s into binary relocatable object file. The driver goes through the same process to generate sum.o. Finally, it runs the linker program LD, which combines main.o and sum.o along with the necessary system object files to create a binary executable object file program. And that runs LD with the relocatable object files. To run the executable program, we type its name on Linux shell command line prog. The shell invokes a function in the operating system called the loader, which copies the code and data in the executable file prog into memory and then transfers control to the beginning of the program. Static linking. Static linkers such as Linux LD program take as input a collection of relocatable object files and command line arguments and generate as output a fully linked executable object file that can be loaded and run. Getting old. All right. Oh. I think I might cut 30 minutes into my breakfast because I kind of like procrastinated on getting started this morning. The input relocatable object files consist of various code and data sections, where each section is a contiguous sequence of bytes. Instructions are in one section, initialized global variables are in another, and uninitialized variables are in yet another section. To build the executable, the linker must perform two main tasks: symbol resolution, object file is defined, and reference symbols, where each symbol corresponds to a function, a global variable, or static variable. Declared with the static attribute. Let me reread this. Step 1, symbol resolution. Object files define and reference symbols, where each symbol corresponds to a function, a global variable, or a static variable, i.e. a C variable declared with a static attribute. The purpose of symbol resolution is to associate each symbol reference with exactly one symbol definition. Relocation. Compilers and assemblers generate code and data sections that start at address 0. The linker relocates these sections by associating a memory location with each symbol definition and then modifying all of the references to those symbols so that they point to this memory location. The linker blindly performs these relocations using detailed instructions generated by the assembler called relocation entries. The sections that follow describe these tasks in more detail. As you read, keep in mind some of the basic facts about linkers. Object files are merely collections of blocks of bytes. Some of these blocks contain program code, others contain program data, and others contain data structures that guide the linker and loader. A linker concatenates blocks together, decides on runtime locations for the concatenated blocks, and modifies various locations within the code and data blocks. Linkers have minimal understanding of the target machine. The compilers and assemblers that generate the object files have already done most of the work. Object files. How big is this chapter, by the way? And we covered it in one lecture. It's it's only 40 pages. Okay, I can get through this today easy. Object files come in three forms. Relocatable object file contains binary code and data in a form that can be combined with other relocatable object files at compile time to create an executable object file. Executable object file contains binary code and data in a form that can be compiled directly into memory and executed. Shared object file, a special type of relocatable object file that can be loaded into memory and linked dynamically at either load time or runtime. Compilers and assemblers generate relocatable object files, including shared object files. Linkers generate executable object files. Technically, an object module is a sequence of bytes. And an object file is an object module stored on disk in a file. However, we use these terms interchangeably. I've never heard of the term object module before. I'll highlight that. Object files are organized according to specific object file formats, which vary from system to system. The Unix system from Bell Labs used the A.out format. To this day, executables are still referred to as A.out files. Windows use the portable executable format. I think COFF is the actual format behind PEs. Mac OS X uses Mach-O format because of the Mach kernel. Modern x86, 64, Linux, and Unix systems use executable and linking format ELF. Although our discussion will focus on ELF, the basic concepts are similar regardless of the particular format. So we got our ELF header, we got our different sections, and we got a section header table. Relocatable object files. Figure 7.3 shows the format of a typical ELF relocatable object file. The ELF header begins with 16-byte sequence that describes the word size, the byte ordering, and the system that generated the file. The rest of the ELF header contains information about that allows the linker to parse and interpret the object file. This includes the size of the ELF header, the object file type, e.g. relocatable, executable, or shared, the machine type, the file offset and of the section header table, and the size and number of entries in the section header table. Locations and sizes of the various sections are described in the section header table, which contains a fixed size entry for each section in the object file. Sandwiched between the ELF header and the section header table are the sections themselves. A typical ELF relocatable object file contains the following sections: text, such as machine code of the compiled program; RO data, read-only data, such as format strings, so any string constants, any constants in general, and jump tables for switch statements. The data, which is initialized, global, and static C variables. Local C variables are maintained at runtime of the stack and do not appear in either the data or BSS sections. BSS is uninitialized global and static C variables, along with any global or static variables that are initialized to 0. This section occupies no actual space in the object file. It is merely a placeholder. Object file formats distinguish between initialized and uninitialized variables for space efficiency. Uninitialized variables do not have to occupy any actual disk space in the object file. At runtime, these variables are allocated in memory with an initial value of 0. Aside, the use of the term .bss to denote uninitialized data is universal. It was originally an acronym for the block started by symbol directive from the IBM 704 assembly language circa 1957, and the acronym has stuck. A simple way to remember the difference between data and BSS sections is to think of BSS as the abbreviation for better save space. Okay, we've got a symbol table, which is a symbol table with information about functions and global variables that are defined and referenced in the program. Some programmers mistakenly believe that a program must be compiled with a -G object to get a symbol table information. In fact, every relocatable object file has a symbol table in the symtab section unless the program has specifically removed it from with the strip command. However, unlike the symbol table inside a compiler, the .symtab symbol table does not contain entries for local variables. This symbol table is necessary for linking. If you don't have this symbol table, you can't link. rel.text, a list of locations in the text section that will be needed to be modified when the linker combines the object files with other files. In general, any instruction that calls an external function or references a global variable will need to be modified. On the other hand, instructions that call local functions do not need to be modified. Note the relocation information is not needed in executable object files, and is usually omitted unless the user explicitly instructs the linker to include it. Rel data, same thing for data. Relocation information for any global variables that are referenced or defined by the module. In general, any initialized global variable whose initial value is the address of a global variable or externally defined function will need to be modified. Debug, a debug symbol table with entries for local variables and type defs defined in the program, global variables defined and referenced in the program, and the original C source file. It is only present if the compiler driver was invoked with -G option. So that's your dwarf debug information. .line, a mapping between line numbers in the original C source program and the machine code instructions in the text section. It is only present if the compiler driver is invoked with -G option. Stir tab, a string table for the symbol table in the sim tab. And debug sections, and for the section names in the section headers, a string table is a sequence of null terminated character strings. Symbols and symbol tables. Each relocatable object module M has a symbol table that contains information about symbols that are defined and referenced by M. In the context of a linker, there are 3 different kinds of symbols. Global symbols that are defined by module M and that can be referenced by other modules. Global linker symbols correspond to non-static C functions and global variables. Global symbols that are referenced by module M but defined in some other module, such symbols are called externals and correspond to non-static C functions and global variables that are defined in other modules. Local symbols that are defined and referenced exclusively by module M. These correspond to static C functions and global variables that are defined with the static attribute. These symbols are visible anywhere within module M but cannot be referenced by other modules. It is important to realize that local linker symbols are not the same as local program variables. The symbol table in SymTab does not contain any symbols that correspond to local non-static program variables. These are managed at runtime on the stack and are not of interest to the linker. Interestingly, local procedure variables that are defined within the C static attribute are not managed on the stack. Instead, the compiler allocates space in data or BSS for each definition and creates a local linker symbol in the symbol table with a unique name. For example, suppose a pair of functions in the same module define a static local variable x. So we've got 2 with different initializations. In this case, the compiler exports a pair of local linker symbols with different names to the assembler. For example, it might use x.1 for the definition of function f and x.2 for the definition of function g. Symbol tables are built by assemblers using symbols exported by the compiler into the assembly language.s file. An elf symbol table is contained in the SymTab section. It contains an array of entries. Figure 7.4 shows the format of each entry. The name, let's look at the format real quick since they referenced it. So we got a struct called elf64 symbol. So we got a name, which is the string table offset. So it's gonna be an integer. It's gonna be offset into the simster. Is it simster section or stir tab? Sorry, stir tab section. And then we got a char type 4. What does that :4 mean? I'm not familiar with the syntax. Let's ask AI. What is the :4 syntax here, and is it valid? C. I've never seen that before. It's declared as 2 bit fields packed into a single underlying storage unit. So you got type uses 4 bits, binding uses 4 bits. Since a char is typically 8 bits, both fields together exactly fill 1 byte. I mean, that makes sense. Why use built fields? Built fields are used to pack small values tightly, match binary formats like ELF network protocols, hardware registers. In your case, this struct looks like it modifies an ELF symbol table where type is a symbol type and binding is okay. These actually small enums, perfect for 4 bits each. Important details. Caveats: not strictly portable layout. The C standard allows compilers flexibility in bit ordering, alignment, and padding. So the exact layout may vary between compilers and architectures. Underlying type matters. You wrote char type 4. I didn't write this. Binding 4, technically valid, but the standard only guarantees built fields for int, unsigned int, and bool. Char bit fields are implementation defined. Safer version would be to say an unsigned char type 4, or more commonly an unsigned int type 4. I guess it doesn't matter what the type is, because I guess you would have extra padding though. Cannot take address of bit fields. It's illegal. Yeah, that's exactly what I was getting at. So access works like normal though, so you can write to it normally. Why this appears in ELF structs. The ELF format used on Linux defines a byte like this. A struct is just a more convenient way to represent that packed byte. Okay, technically we're into breakfast time, so I'm just gonna cut this down to 8:30 to 9. I'm gonna have a really quick breakfast, and then I'm gonna extend my stream here to 8:30. I am a bit hungry, so I will be eating breakfast, but I'm gonna do it really quickly. All right, that's interesting. I haven't seen that syntax before, so it's good to run into it. Okay, so we have our type and our binding. So type is function or data, and binding is local or global. Then we have a reserved byte, and then we have section header index. So that's which section this symbol belongs to. And then we have the section offset or absolute address. So it's going to be either an offset from the section or absolute address of the symbol. And then a size, which is how many bytes it spans. Okay, let's go back to the text. The name is a byte offset into a string table that points to a null terminated string name of the symbol. The value is a symbol's address. For relocatable module, the value is an offset from the beginning of the section where the object is defined. For executable objects, the value is an absolute runtime address. The size is the size in bytes of the object. The type is usually either data or function. The symbol type can also contain entries for the individual sections and for the path name of the original source file. So there are distinct types for these objects as well. The binding field indicates whether the symbol is local or global. Each symbol is assigned to some section of the object file, denoted by the section field, which is an index into the section header table. These are three special pseudo sections. There are three special pseudo sections that don't have entries in the section header table. So that's ABS for a symbol that should not be relocated. Undefined is for undefined symbols, that is, symbols that are referenced in this object model but defined elsewhere. And common for uninitialized data objects that are not yet allocated. For common symbols, the value field gives the alignment requirement and size gives the minimum size. Note that these pseudo sections exist only in relocatable object files. They do not exist in executable object files. The distinction between common and BSS is subtle. The distinction between common and .bss is subtle. Modern versions of GCC assign symbols in relocatable object files to common and BSS using the following convention. So uninitialized global variables go in common, but then uninitialized static variables and global or static variables that are initialized to 0 go in BSS. Okay. New to C, hiding variable and function names with static. C programmers use a static attribute to hide variables and function declarations inside modules, such much as you would use public or private declarations in Java and C++. In C, source files play the role of modules. Any global variable or function declared with a static attribute is private to that module. Similarly, any global variable or function declared without the static attribute is public and can't be accessed by any other module. It is good programming practice to protect your variables and functions with the static attribute wherever possible. All right. The reason for this seemingly arbitrary distinction stems from the way the linker performs symbol resolution, which we'll explain in section 7.6. Oh wow, we're already in section 7.6. Wow. Just cruising through this. The GNU readelf program is a handy tool for reviewing the contents of object files. For example, here are the last 3 symbol table entries for the relocatable object file main.o. From the example program in figure 7.1, the first 8 entries which are not shown are local symbols that the linker uses internally. Actually, let's fix up our to make clean jobs. There we go. This main here, we need to fix that up. So we're going to do, similar to sum, we're going to do a main.o. Main.o main.c, and yeah, basically does the same thing there. And then this is going to take build main.o, and yep. So the relocatable object relocations. So we have rela debug line, rela eframe, rela debug info, rela text. It's funny, these are called rela, whereas in the book they refer to them as rel.data. Rel.text. And what are they looking at here? The first 8 entries, the readoff program is a handy tool for reading the contents of object files. For example, here we are the last 3 symbol table entries for the relocatable object file main.o from the example program figure 7.1. The first 8 entries which are not shown are local symbols that the linker uses internally. So we want to look at the symbol table here. So you have main array and sum, func object no type, global default, size. Interesting that they keep a undefined thing here. In this example, we see an entry for the definition of global symbol main, a 24-byte function located at the offset 0 of the text section. This is followed by a definition of global symbol array, an 8-byte object located at an offset 0 in the data section. The last entry comes from the reference to the extra symbol sum. Readoff identifies each section by an integer index. 1 denotes the text section, 3 denotes the data section, and undefined denotes it's external to this module. Do I want to do the practice problems for this? Let's see how crazy they are. I do like playing with linkers. I think I'm gonna learn a good amount. We did want to spend more time with this, and the practice problems, frankly, are not insane. And they're probably going to give me a good amount of experience. Yeah, there's very few practice problems. Yeah, there's 5 of them. I'd be doing myself a disservice if I didn't go through these. Okay, and then there's homework problems here too. Okay, set my bookmark there. We have 15 minutes for breakfast. Let's do the practice problem. Okay. This problem concerns m.o and swap.o modules from figure 7.5. Where's 7.5? Oh, that's down below here. Okay, let's go ahead and write this out. Vim m.c is a void swap, and we'll do that as a header file. Pound include swap.h main, yeah. And then here we have a int buff2, and it's initialized to 1.2. And here we call swap, and we return 0. Yep. Then swap.c, we have an extern int buff, and then we have a int pointer buff p0, which equal to a pointer to buff 0, which is the same thing as buff. And we have int pointer buff p1, and then down here we have a void swap, and the implementation is to say int temp, and we say buff p1 is equal to ampersand of buff 1, and temp is equal to the read of buff p0. And then we read from buff p0. You don't need to do all this stuff with globals. Buff p1, and then star buff p1 is equal to temp. And that could be done up here as well, and this whole thing could be local. It's very weird. They're doing it just to show the linking though. Let's copy swap.c to swap.h, and we'll just delete everything. Oops. And then we'll bring up our make file here. Do the same thing here. Oops. Well, we need to say, hey, build m dot, just m. And then this is going to be build m is actually m.o and swap.o. And then we have a similar thing going on here, where we have m.o comes from m.c, and swap.o comes from swap.c. Make. Okay, so I built everything. This program considers m.o and swap.o modules from 7.5 for each symbol that is defined and referenced in swap.o. Indicate whether or not it will have a symbol table entry in symtab section in module swap.o. If so, indicate the module that defines the symbol type, and the section in the assigned to the module. Okay. So I'm not gonna cheat and look at the readelf, but I will do that after I'm done making my guesses. Markdown table generator, and we got 1 2 3 4 5 by 1 2 3 4 5 6. File new, 5 by 6. And here we got symbol dot symtab entry, symbol type module where defined section, and we'll say buff, buff p0, buff p1, swap, and temp. Go down generates, copy to clipboard, then problems dot md. This will be 7.1, and let's reread the problem statement here. So we got, for each symbol that is defined or referenced in swap.o, okay, indicate whether or not it will have a symbol table entry in the symtab section of the module swap.o. If so, indicate the module that defines the symbol, swap.o or m.o, the symbol type, local, global, or extern, and the section, text, data, BSS, or common, and it is assigned to in the module. So symbol table entry for buff, yes. Yes. Oops. Symbol type, it's external. Module where it's defined is m.o. And the section will be in the section in swap.c or in the section in swap.o or the section in m.o. I'm not really clear about that. But the section will be ultimately in a, I think, data section. It's definitely not text. It could be data, BSS, or common. Common is uninitialized global variables. BSS is uninitialized static variables or global or static variables that are initialized to 0. I think it's data. Okay. Let's check that first one. Okay, buff, yes, external, m.o, and data. Cool, got it right. Alright, buff p0. Yes. Buff p0 is not external. Buff p0 is a it's defined in swap.o. What is its symbol type? Local, global, or extern? It's gonna be a global. global, and its section is going to be definitely .data because it's initialized. Let's look here. Yes, global swap data. Yes, global swap data. Yep. Buff P1. So it's uninitialized. It definitely has a simple table entry. It is still a global. It is still in swap.o. Now this one might be in BSS or common. Looks like it's common. Uninitialized global variables going common. Distinction between common. So let's review common here. Common is for uninitialized data objects that are not yet allocated. For common symbols, the value field gives the alignment requirement, and size gives the minimum size. Note that these pseudo-sections exist only in relocatable object files. They do not exist in executable object files. Distinction between common and BSS is subtle. Modern versions of GC assign symbols in relocatable object files to common and BSS using the following convention. Common is for uninitialized global variables. BSS is uninitialized static variables, and global or static variables that are initialized to 0. Basically all the 0 stuff goes into BSS, except for uninitialized global variables go into common. Okay. Well, according to that convention, then this goes into common. Okay, let's check that. Yes, global swap common. Yes, global swap common. Great. Okay, swap is yes. Symbol type is going to be global. Swap.o. And it's going to be in text. So that's yes, global swap text. Yes, global swap text. Yep. And then finally temp, which is just a local stack thing. So there's no symbol table entry. I think I want to do it like that. Symbol type will be local. Well, this will just be like, okay, there's no symbol table entry. It would be local, but there's no entry. Module, well, it is a local, but local implies that it's a static global, but fuck it, we'll say local. Oh. So I got 4 minutes remaining here, and then I'll break for breakfast. Okay, so modules were defined. It would be in swap.o, obviously. Swap.o. And the section would be... It's not going to have a section. Dash, I guess. because it's on the stack. I question whether this should even be simple type local, because locals are really globals that are static, or functions that are static. But stack local variables are not, they don't have symbols, so they don't really have a symbol type. Yeah, exactly. They just put dashes there. So I'll go ahead and put my dashes back, because there's no symbol table entry, so you can't have any of these values. Cool. Alright, that is that. We got 2 minutes. Maybe I'll just break here and resume at symbol resolution when I get back from breakfast. Cool. Well, this is fun. I got the 7:15 with doing all the problems. So that's 10 pages in a little over an hour and a half. So I'm happy with that progress. Half of this, 30 minutes of this was just like chatting about Ghidra. So it's really an hour. So 10 pages an hour. It's not insane progress. I could have made more progress in that time, but it is what it is. So I will come back after breakfast and start on the symbol resolution section. All right. I'll be back in 30 minutes. Later.